Okay, hi everyone, welcome back to this video series on the Comptia Security Plus course, LANMAN. The LANMAN hash, also known as the LAN Manager hash or simply LM hash, was the original hash used to store Windows passwords. It was used in Windows operating systems before Windows NT, but is supported by some versions of Windows in an attempt to be backward compatible. This backward compatibility can be a security risk because the LM hash has several weaknesses and can be cracked easily. Its function is based on the deprecated DES algorithm and can only be a maximum of 14 characters. These weaknesses are compounded by the fact that the ASCII password is broken into two pieces, one of which is converted to uppercase, essentially removing a large portion of the character set. Plus, it can store a maximum of only 7 uppercase characters. Due to this, brute force attacks can crack alphanumeric LM hashes in a matter of hours. Due to all these weaknesses, it is highly recommended that the LANMAN hash be disabled on operating systems that is run by default. It should also be checked on operating such as Windows Vista, Server 2008 and higher that are supports to have it disabled by default, just in case the setting was modified. The following step-by-step procedure shows how to disable the storage of LM hashes in Windows. Open the run prompt, type secpool.msc to display local security policy window. Step 2, navigate to local policy security options. Step 3, in the right pane, double click the policy named network security. Do not store LAN hash manager value on next password change. Click enabled if it isn't already, as shown in figure 14.3, and then click OK. You can also disable the storage of LM hash passwords by modifying the registry. This process is necessary for older versions of Windows. For more information, see the link to Microsoft's website in the View Recommended Resources document on the accompanying website. If for whatever reason the storing of LM hashes for passwords cannot be turned off, Microsoft recommends using a 15-character minimum password. When this is done and LM hash and the NTML hash value are stored in this situation, the LM hash cannot be used solely to authenticate the user. Therefore, it cannot be slowly cracked. The NTML hash would have to be cracked as well, because 15 characters might be beyond some organizations' policies or some users' ability. For that matter, it is highly recommended that the LM hash policy be disabled. NTML and NTMLv2. Well, we talked a lot about why the LM hash is insufficient. Let's get into the replacements. The first is the NTML hash, also known as NT-LAN hash. Also known as the NT-LAN Manager hash. The NTML algorithm was first supplied with Windows NT 3.1. It provides Unicode support and, more important to this conversion, the RC4 cipher. Although the RC4 cipher enables a more powerful hash known as NTML for storing passwords, the systems it ran on were still configured to be backward compatible with the LM hash. So as long as the LM hash was not disabled, those systems were still at the same risk as older systems that ran the LM hash only. Windows Vista and Windows Server 2008 operating systems and higher disable the older LM hash by default, while NTML uses cyclical redundancy checks (CRC) and message digest algorithms for integrity. The main issue with NTLM is that it was based on the RC4 cipher and not any recent cryptographic methods such as AES or SHA-256. RC4 has been compromised, and therefore the LTLM hash is compromised. Due to the weakness of NTLM, we need a stronger hashing algorithm, NTMLv2. The NTMLv2 hash uses an HMAC MD5 hash, making it difficult to crack. It is a 128-bit system. NTMLv2 has been available since Windows NT 4.0 SP4 and is used by default on newer Windows operating systems. Even though NTMLv2 responds to the security issues of the LM hash and NTLM, most Microsoft domains use Kerberos as the login authentication scheme because of its level of security when dealing with one computer logging into another or into an entire network. Domain NTMLv2 is used either when Kerberos isn't available, users log in with local accounts, or are connecting. OS doesn't support Kerberos. Hashing attacks. A cryptographic hash is difficult to reverse engineer but not impossible. A powerful computer can decrypt some hashes. It just takes time. But time is of the essence, and so attackers will attempt other methods such as creating collisions, using side channel attacks, or utilizing a privilege escalation. Let's discuss a couple of ways that hashes can be exploited. Pass the hash. A pass the hash attack is when an attacker obtains the password hash of one or more user accounts and reapplies the hash to a server or other system in order to fool the system into thinking that the attacker is authentic. The goal is for the attacker to gain access to the system, often a Windows server, and gain another user's credential with the potential to escalate privileges. The attack starts with the attacker obtaining the hashes from a target system. That's the hard part. Access to the system is required in one way or another. Then the attacker can use a hash dumping utility to collect the hashes for user passwords. Next, the attacker utilizes a pass the hash program to place the hashes within the server, for example within the local security authority subsystem service LSASS in Windows Server. This can be done using a side channel attack so that the attacker can impersonate one of the users. If done properly, the attacker does not need to know the password of the account, does need to brute force the password, and does not need to reverse engineer the hash. While the attack can be carried out on an individual client system also, it is more often something that is focused on Windows servers, namely domain controllers, because they house many user account credentials. Prevention includes the following: only allowing clients that are trusted operating systems to connect to a server, configuring Windows domain trusts securely, using multi-factor authentication, using tokens, and implementing the principle of least privilege for user accounts. When employing least privilege, be sure to include domain accounts and local admin accounts. Finally, standard network security should also be implemented, including IDS and IPS solutions, firewall restrictions, and so on. Happy birthday. Not when a birthday attack is involved. A birthday attack is when an attack on a hashing system that attempts to send two different messages with the same hash function, causing a collision. It is based on the birthday problem in probability theory, also known as the birthday paradox. This can be summed up simply as the following. A randomly chosen group of people will have a pair of persons within the same calendar day birthday given a standard calendar year of 365 days. The probability of this occurring with 366 people is 100%. 367 people on a leap year. So far this makes sense and sounds logical. The paradox thoughtfully and mathematically comes into play when fewer people are involved. With only 57 people, there is a 99% probability of a match, a much higher percentage than one would think, and with only 32 people there is a 50% probability. Imagine that and blow out your candles, and by this I mean use hashing functions with strong collision resistance, because if attackers can find any two messages that digest the same way, use the same hash value, they can deceive a user into receiving the wrong message. To protect against a birthday attack, use a secure transmission medium such as SSH or encrypt the entire message that has been hashed. Additional password hashing concepts. Remember that hashed passwords are one-way functions. The process of hashing takes the password and converts it into a fixed length binary value that cannot be reversed. The converted number is usually represented in hexadecimal due to its nature of the conversion. Even slightly different passwords will have completely different hashes. Know that password hashes can be cracked. I said the number cannot be reversed, and it can't, because it is a one-way function, but the hash can be cracked in a variety of ways. A person could try to guess the password, or use a dictionary attack method, or try the brute force attack method. Attackers will also make use of lookup tables, reverse lookup tables, and rainbow tables. These vulnerabilities make your password policies and type of hash you use very important. Of course, in some scenarios you might be limited as to the length of password you can have your user select. For example, let's say you are using a web server technology with a somewhat weak password methodology, and you are concerned about hash collisions. There are other ways to increase security of the password. One way is to use key stretching. A key stretching technique will take a weak password, process it, and output an enhanced and more powerful key. Often this process will increase the size of the key to 128 bits, making attacks such as brute force attacks much more difficult, if not impossible. Examples of key stretching software include PBK, DF2, and bcrypt. These utilities also incorporate salting to protect against dictionary attacks, brute forcing, and rainbow table attacks. Salting is additional random data that is added to a one-way cryptographic hash. It is one character or more, but defined in bits. The person with the weaker web server password, or perhaps the admin with the NTLM hash, would do well to consider key stretching or salting. Another technique is the use of nonce number used once. It can be added to password-based authentication schemes where a secure hash function such as SHA is used. It is a unique number that is difficult for attackers to find, that can only be used once. As such, it helps to protect users from replay attacks. Of course, an admin needs to remember that the primary line of defense when it comes to passwords is to use complexity and length, not just one or the other. There are a couple of myths connected with passwords in general. The first is that complexity is better than length. this isn't always true. It will depend on the type of attack, dictionary or brute force, the level of complexity and the length of the password. So again, if at all possible, define policies that specify. This is always true. It'll depend on the type of attack. I'm after losing where I am. There's always a couple of myths connected with passwords in general. The first is that complexity is better than length. This isn't always true. It'll depend on the type of attack, dictionary or brute force, the level of complexity and the length of the password. So again, if at all possible, define policies that specify complexity plus length. And if length cannot be incorporated into your password scheme, use key stretching or salting to consider using a different hash altogether. Another myth is that password checkers ensure strong password. Password checkers can help you get an idea of whether a password is secure, but may interpret some weak passwords as strong. Remember also to limit the number of times that a password can be tried via policy. For example, limiting password attempts to 5 or even as little as 3. Remember the 3 strikes and you're out rule. Also define delays between consecutive password attempts. This is especially important on websites. It can help to defend against exhaustive key searches. Better yet, use one-time passwords, OTPs, such as HMAC-based OTP, HOTP. Extend that concept by supporting a time-based moving factor that must be changed each time a new password is generated. And you have the time-based OTP, TOTP. It may seem like we've covered a dazzling array of password technologies and acronyms, but we can quickly get our bearings by creating a checklist and going through it every time we design a password scheme. Use a strong hash, and if not possible, utilize key stretching, incorporating salting, consider OTPs, and create meticulously defined policies governing passwords. Finally, if working on a website that accepts passwords, especially public passwords, implement secure programming techniques, particularly input validation. Chapter summary. If there's one thing you should take away from this chapter, it's that my phone number was probably never in any black books, either as plain text or as ciphertext. Just making sure you are reading the chapter summaries. Be thankful I am not advertising computers this time. Seriously though, it's amazing how many children can easily understand and design code with which to hide information. It's not surprising that there are so many cryptographers and cryptanalysis in this day and age, and a huge assortment of ciphers to work with. The art of secret communication can basically be broken down into 2 categories: steganography and cryptography. Both have been useful for millennia, but one is inherently insecure and the other is inherently crackable. Steganography hides the entire message, but if the message is found, the message is instantly compromised. Remember the discussion of the Greek messenger who shaved his head, had a message written on his scalp and regrew his hair. If he had been asked by a guard at the border to shave his head and had complied, the message would have been seen right away. That's why insecurity is built right into the scheme. Cryptography, on the other hand, is used to hide the meaning of a message. The message could be there for everyone to see, but they won't understand it unless they have a key to the message. Of course, all ciphers can be cracked. It's built into their DNA, so to speak, but without the proper key size and the appropriately designed ciphers, it can be very difficult, if not impossible, to crack the code. So encryption is the weapon of choice for most data transfers. However, you will see some scenarios where a message is encrypted and then hidden as well, effectively combining the two concepts of cryptography and steganography. For example, user A might email user B with an attachment containing a photo of the Grand Canyon, a slightly altered Grand Canyon, where some of the pixel colors have been changed, but the changes are not visible to the naked eye. User B already has an altered version of the original photo stored on the computer. User B compares the two and locates all the modified pixels, or has a program to do it. The modified colors could translate to letters in the alphabet. For example, a certain shade of red 3-byte color would be written numerically as FF006625500102 in decimal. It could have been decided earlier that the third number of the 3 bytes would be the modified color. Furthermore, 102 is equal to the letter F in ASCII, which might be the first letter of the first sentence of a message. The process would continue until the complete message emerges from a group of modified colors. That's pretty hidden, wouldn't you say? But now, encryption could be employed based on a predetermined code. It could be as simple as a Caesar cipher where the letters are shifted over 3 places. So instead of the cipher text F, we get the plain text C. So now the message is hidden and the meaning of the message is hidden, and we can get as complex as we want with the cipher, either by utilizing a published algorithm or by designing our own. Dating back to ancient times, cryptographers would create a code and cryptanalysis would attempt to crack it. Every time a code was cracked, it was then considered compromised and a new code would be created. This concept has been even more pronounced during the computer age. That's why there are so many algorithms in this chapter. The Silic mousetrap effect has been in play for decades. Symmetric algorithms using a single key or more than one identical key or similar keys. One of the most powerful symmetric algorithms is the advanced encryption standard AES, which can have a maximum key length of 256 bits. That is considered uncrackable. So instead of trying to crack the code, attackers will usually attempt to maneuver around it and assault the implementation of the algorithm. Asymmetric algorithms, on the other hand, use a pair of different keys for encryption and decryption. For instance, take public key cryptography, where there will be a well-known public key that is used to encrypt messages, and a secret private key is used to encrypt them. A common example of an asymmetric algorithm is RSA. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.